Hi, everybody. Welcome back to Chapter 8, Part 2. We've been talking about hypothesis testing. So today we're just going to basically review what we were talking about last time with a new example and make sure that you're clear about what a sampling distribution is, because, boy, that's important. It's really important. So this is what we talked about last time, right? In order for you to analyze statistics, there's two steps. The first step is make sure you know what statistic you're supposed to run. Now this depends on whether it's categorical, continuous, how many variables you have, how many levels of the variables, of the categorical variables, if you have those, that depends. And so we're going to practice those. Different ones have different things. Then the step two is once you calculate that statistic, you got to figure out the probability of getting that on the sampling distribution. So what you do is you evaluate that statistic based off the sampling distribution. So let's say that I calculated the statistic in step one and I got a value of 28, right? Then the step two is, hey, looking at the sampling distribution, what's the probability of getting a 28 if the null hypothesis is true, right? So that subsection says if the probability of getting an obtained statistic, 28, or something more extreme, right, more than 28, is less than or equal to alpha, then you reject H sub 0, and H sub 0 is the null hypothesis. Remember, alpha is whatever standard you happen to accept. Normally, we think about this as 0.05, right? It's a 5% chance of making a type 1 error. So let's do an example of this, but starting with the idea of the null hypothesis population. So you realize that all we're doing here is we're comparing what we got to what we would expect if the null hypothesis is true. So the null hypothesis population is an actual or theoretical set of population scores that would result if the experiment were done on the entire population and the IV had no effect, right? IV had no effect, that's null hypothesis, right? The null is true. So what we got to do is we got to think about, hey, here's what I got. What would I expect if the null was true, if nothing was going on? If glasses had no effect on being hot, right? The null hypothesis population would be everybody's hotness score if glasses had no effect on your hotness. That would be the null hypothesis population. And we would be able to see everybody's hotness score, and therefore we would know the probability of getting any given hotness score if glasses had no effect on your hotness. Let's go through an example of this with Teenage Mutant Ninja Turtles. So there's a population of 4 Teenage Mutant Ninja Turtles. That's all, in the entire population. Leonardo, Michelangelo, Donatello, and Raphael, those are the 4 in the entire population. That's the whole population. So this first one right here, that's Leonardo, right? And let's get some information about a couple of variables. So whether or not his weapon is metal or wooden. So he has katana blades, that's a metal weapon, right? This is Michelangelo. He used nunchucks, that's mostly wood. Donatello has a bow staff, he's mostly wood. And Raphael has a sai, that's a metal weapon. Got it? Okay, so this is the entire population. This is not a sample. This is the whole population. Also, Leonardo over here, he eats 1 pizza a day. That's just what he does. That's how much he eats. Michelangelo eats 5 pizzas every day. Donatello eats 3 pizzas every day. And Raphael eats 2 pizzas every day. Every day. Every day. That's what he's doing. That's normal. This is the whole population. The whole population has 4 turtles in it. All 4. That's the whole population. Everybody. This is everybody. This is not a sample. It's everybody. That's an important point. Let's keep moving and start talking about some things. So let's start talking first about this metal versus wooden weapons. These are the same data that I just barely showed you, just in a table form. So Leonardo has a metal weapon and eats 1 pizza. Donatello has a wooden weapon, eats 3 pizzas, etc. Okay, same data. That's the same data for the entire population. This is the whole population. Whole population. Now, if I sampled 2 turtles, what's the probability that one has a metal weapon and one has a wooden weapon? So let's think about this. Here's how you do this. Okay, we're talking about a random sample. This is a totally random sample, and each time you sample, you're sampling from all 4 turtles. So think about it like this. Let's say that On Monday, I randomly sample one of the turtles. I randomly choose one of the turtles. Okay, and then on Tuesday, I randomly sample one of the turtles. Right. So on Monday, I take 1 out of 4. And then on Tuesday, the one that I sampled is put back in, right? So it's still 1 out of 4. So in each one of these, we have replacement going on here. We put them back in for the second sample. So in this case, it's totally random sample. Think about it in terms of like on Monday, it's going to be, I'm going to sample this one. And then randomly on Tuesday, I'm going to sample this one. So if you randomly sampled 2 turtles, what is the probability that one has a metal weapon and one has a wood weapon? That's 0.5. It's 0.5, right? If I take 2 turtles out of 4 turtles, and in real life, look at this. Leonardo has a metal weapon, Raphael has a metal weapon. 2 out of 4 have metal, 2 out of 4 have wood. Then if I take any 2, the probability that half of them would have metal and half of them would have a wooden is 0.5, right? 0.5. Got it? Now, let's keep going with this. Let's keep going. I sampled 2 turtles. What would be the probability that both would have a metal weapon? So, same situation. Take 1 out of 4 turtles on Monday, put them back in. 1 out of 4 turtles on Tuesday. What is the probability that the 2 that you sampled have a metal weapon? Now, there's a few ways we can think about this, right? We can look at the actual probability by just calculating it, right? So the probability that anybody has a metal weapon is 0.5. So at time 1, 0.5. And time 2 metal, so the probability of metal in time 1 is 0.5. The probability of metal of part 2 is 0.5, and day 2 is 0.5. So 0.5 times 0.5, because this is and, right? Metal and metal. 0.5 times multiplication rule times 0.5 equals 0.25. But you can also think about this just by looking at the probabilities in terms of what would happen if you looked at all the possible combinations of a sample of 2 turtles, right? And that's the sampling distribution. A sampling distribution is all the values a statistic can take. So in this particular case, remember, I'm taking a sample of 2 turtles, all right? 2 turtles. What are all the possible values that that sample can take? Well, if we're looking at wood or metal, it could be 1 wood, 1 metal. It could be 2 wood, or it could be 2 metal. Those are the possible values that it could take. Along with their probabilities, if the sampling is random from a null hypothesis population, saying, if everything is normal and you're replacing, what would be the probability? So this is a list of all of the possible samples if n minus 2, right? So I've got only 4 people in the actual population, 4 turtles in the population, right? And if I take a sample of 2 turtles, then here are all the possible samples that I could do. There's 16 possible samples that could happen. I could choose Leonardo on the first day and Leonardo again on the second day. That would mean that I would result in 2 metal weapons. It could be Leonardo on the first day and Donatello on the second day. These are all the possible combinations of n equals 2. So these are all the possible samples when n equals 2 and the possible results. So 2 metal, 1 metal, 1 wood, 2 metal, 1 metal, 1 wood, etc., etc., etc. So here's what we're going to do. Let's go ahead and look at this in terms of a distribution, right? So we'll just make a small one over here on the side. Let's see if we can make this work. So we're going to make a histogram, essentially. All right, we're going to make a histogram. And so the possible ones that we have, and let's just do this in terms of number of metal weapons. Okay, the number of metal weapons. One possibility is 0 metal weapons. One possibility is 1 metal weapon, and one possibility is 2 metal weapons. So if I got wood, that would mean I'd have 0 metal weapons. If I have 1 metal weapon, then it could be 1 metal, 1 wood, or 1 wood, 1 metal, right? Those are the possibilities. 2 metal weapons is 2 metal weapons. Got it? So it's the same information that we've got here in the results column, same stuff. Then over here, we're going to have the frequency. So this is going to be frequency, spelled really poorly, frequency, right? And the different frequencies that we could have. So let's take a look at this. There's a total of 16 samples that can be done. Total of 16 samples. There's 16 ways that you've got 4 turtles. You can take 2 of them. There's 16 possible samples that could happen. All right? So let's start backwards and look at the number of 2 metal weapons. So 2 metal weapons, 1, 2, 3, 4. 4 out of 16, right? So all I was looking for is the frequency of 2 metal weapons, the frequency of 2 metal weapons. Here it is, 1, 2, 3, 4. The possibility of that happening, there's 4. So let's go ahead and I guess we'll need to make this bigger, but 1, 2, 3, 4, 5, 6, 7, 8. Let's take this all the way up to 8. See if that'll work. All right. So 2 metal weapons, the probability of that happening is 4. Okay. There it is. Notice how we're making a histogram, right? Now, what is the frequency of 1 metal weapon? So sample number 2 has 1 metal weapon. 4 has 1 metal weapon. 6 has 1 metal weapon. 7, 10, 12, 13, and 15. 8. There's 8. 8 of them. So the frequency of 1 metal weapon would be 8. Okay? Let's see if that works. There it is. And those bars are supposed to be touching because this is a histogram. Well, guess what? Let's look at the frequency of 0 metal weapons. So that means 2 wood weapons. So the frequency of 2 wood is 1. So sample number 5, sample number 8, sample number 14, and sample number 16. There's 4 that have 0 wood. So the frequency of 0 wood is 4. All right. So look at this. Now, remember, this distribution that you see right here is a sampling distribution. It is all the possible outcomes of an n equals 2 sample, all the possible outcomes of how many metal weapons are going to happen. These are all the possibilities, all of them, total. So what we can do is we can take that frequency and change it into a probability. Remember, these are all the possibilities, so there are 16 possibilities. 4 divided by 16, or 16 divided by 4, is 0.25, right? So 4 divided by 16 is 0.25. It's a 25% chance, right? So the probability of 0 metal weapons, probability of 0 is 0.25. The probability of 1 is 8 out of 16, which is half, 0.50. And the probability of 2 is 0.25. 4 divided by 16, right? So look, if you want to think about it, just count these up. 4 out of 16 possibilities had 2 metal weapons. 8 out of 16 possibilities had 1 metal weapon. And 4 out of 16 possibilities had 0 metal weapons, right? So the probabilities, 4 out of 16 is 0.25, 8 out of 16 is 0.50, and 4 out of 16 is 0.25. Okay? This is a list of all the possible outcomes. So these results, this all the possible outcomes and the probability of them happening, right? The probability of each of them happening. This is a sampling distribution, right? All the possible outcomes and the probability of them happening. Now, here's what we're going to do. Let's take a look at this. Does this look familiar? This is the binomial distribution. When 50% of the population have metal weapons, right? And we're looking at a sample of 2, the probability of 0 people having a metal weapon is 0.25. The probability of 1 having a metal weapon is 0.50. The probability of 2 having a metal weapon is 0.25. Got it? So this, let's see if I can mark it up. I'm not sure that I can. Yeah, it's not gonna let me do it. This is this part right here, 0.25, 0.5, and 0.25. That is a sampling distribution. Just that little part right there. That is a sampling distribution. That is it. So let's see if I can actually, no, don't worry about it. I was gonna see if I can mark it up. But this is a sampling distribution. Notice how the sampling distributions are different depending on how big is your n, right? This is just saying if you take a sample of two turtles, what's the probability that 0 of them will have a metal weapon if 50% of the population has metal weapons? And the probability of 0 people out of 2 having a metal weapon is 0.25. It is the same information as this right here. It is the same information as this. It is the same thing. Same thing. Same stuff. The tables are sampling distributions. They're sampling distributions. So let's take a look at another question. With n equals 2, what is the probability that 1 or more of the turtles will choose a metal weapon? So if n equals 2, what's the probability that 1 or more will have a metal weapon? So let's look back at this. Look back at our data, right? Look at our frequency. 1 or more. So what's the probability of 1 or 2 turtles having a metal weapon? It's the probability of 8 out of 16 plus 4 out of 16, which is the probability of 0.5 plus the probability of 0.25. Notice how when we're talking about or more, or we're adding addition rule, or, right? So the probability of 1 or 2 out of a sample of 2 having a metal weapon is 0.75. We can see the same information when we look at the binomial table. What's the probability of 1 or more? So it's this plus anything more than that. So in this case, it's only 1 or 2. We're going to add up the probability of 0.5 plus 0.25, 1 or more. So the probability of 1 or more people having a metal weapon is 0.75, 1 or more. Okay, let's go back to this, because all we've talked about so far is just this idea of a sampling distribution. And what about that whole hypothesis testing? Where's my hypothesis? Here's a hypothesis. Let's say that Shredder, so Shredder is the enemy of the Teenage Mutant Ninja Turtles. Let's say that Shredder finds a way to set himself on fire and fight while he's on fire. So the Teenage Mutant Ninja Turtles got this whole week coming up ahead of them where every day they're going to have to fight Shredder with Shredder being on fire. Got it? So Shredder's going to be on fire the whole time. My hypothesis is that if Shredder's on fire, the turtles are going to choose metal weapons and not wood weapons. So my hypothesis is if Shredder is on fire, the turtles will choose metal weapons. What is the null hypothesis? The null hypothesis is that Shredder being on fire will not have any effect on whether they choose metal weapons or not. Null. It'll have no effect. Shredder being on fire will have no effect on what kind of weapon they choose. That's the null hypothesis. All right, now, does this that we just looked at, this is the same data, everything that we just looked at, does this represent the null hypothesis or the alternative hypothesis? Remember, the null is that Shredder being on fire will have no effect. The alternative hypothesis is my hypothesis. It says that if Shredder's on fire, I think they're going to choose metal. Does this that you see right here, does it represent the null or the alternative? This represents the null. This is what is normally going on, not because Shredder's not normally on fire. Shredder doesn't just hang around being on fire, right? This is just normally what's going on in the population. This represents the null hypothesis. So when we said the probability of 0 people having a metal weapon being 0.25, that is if the null is true, right? That is if nothing weird is going on. It's strange when Shredder's on fire. That's not the null, that's the alternative. Okay, so that is the sampling distribution, all the possible outcomes, if n equals 2, right? All the possible outcomes is when the null is true. When everything is normal, when nothing strange is going on, when Shredder's not on fire. Okay? That's the null. The sampling distribution is when everything is normal, when the null is true. We can figure out what the probability of that is when the null is true, but since Shredder's not hanging out on fire, we don't know what the probability is when Shredder's on fire normally. So that's why we compare our alternative hypothesis to the null and the probability of it happening when everything is normal. What do I mean by that? Well, let's take a look at it. Let's say I collect some data, right? So let's say, hey, we know that Shredder's going to be on fire. I have a hypothesis that if Shredder's on fire, that the turtles are going to choose metal weapons instead of wooden weapons, right? And so I say, all right, we know that they're going to be fighting Shredder all week long, so they're going to encounter Shredder on fire every day of the week. So on Monday, day 1, I take 1 out of 4 turtles and see whether or not they're using a metal weapon. Then on day 2, take 1 out of 4 turtles and see whether or not they're using a metal weapon, right? N equals 2, okay? So let's say that I found that both times when I picked a sample, when I picked a turtle out, both times they were using a metal weapon. Should I reject the null hypothesis? All right, well, let's talk about this. Let's talk about how we're going to figure this out. So I collected my data. Now remember, we already know what the probability of 0 out of 2 having a metal weapon, that equals 0.25, right? The probability of 1 out of 2 is 0.50. The probability of 2 is 0.25, right? Now remember that these probabilities are if the null is true. If Shredder being on fire has no effect on what weapon you're going to choose. What that's saying is that if I find that 2, when Shredder is on fire, I find out that 2 people, that 2 times, 2 turtles are using metal weapons, 2 out of the 2 are using metal weapons, that means the probability of that happening when the independent variable, Shredder being on fire, has no effect on the dependent variable, what kind of weapon you choose, the probability of that happening when being on fire has no effect on the kind of weapon you choose is 0.25. I have a 25% chance, a 25% chance of the turtles choosing 2 metal weapons when Shredder being on fire has absolutely nothing to do with it. So when you are looking at should I reject the null hypothesis, you're saying, hey, okay, all right, Shredder's been on fire. Hey, I just picked out 2 turtles. They both had metal weapons. Did I find that because Shredder actually is causing a change in what kind of weapons they're choosing? Or is it just by chance? Is it just that, you know, that's normally what's going on, and I just happen to have a 25% chance of that happening? The standard that you are willing to accept, the probability, that's an A, an alpha. The alpha is the probability you're willing to accept of being wrong. The probability you're willing to accept of saying, hey, you know what, Shredder being on fire does affect what kind of weapon you choose, when in reality it doesn't. That is the chance you're willing to take, and you should give it a numerical standard. So let's say that, hey, my standard is going to be, the normal standard is 0.05. Well, that means that if you're only taking 2 people, if you're only taking a sample of 2, no matter what you do, you can never reject the null hypothesis. Because the only possibilities are 0 people have metal weapons, 1 person has a metal weapon, or 2 people have metal weapons. And the probability that 0 or 2 people having a metal weapon is 0.25 when everything is normal. So there's no possible way that you could reject the null hypothesis if your alpha is 0.05, if your standard is a 5% chance. Because at any given moment, the result that you get has at least a 25% chance of happening when Shredder being on fire has nothing to do with the weapon that you choose. What we just did is we calculated the appropriate statistic. Now, in this particular case, we wanted to know what kind of weapon you're going to choose. That is a categorical variable. And it had 2 possibilities, wood or metal. And those were mutually exclusive. When you have a categorical variable with 2 possible outcomes that are mutually exclusive, you can use a binomial. The appropriate statistic to use is a binomial. Then we evaluated that statistic based off the sampling distribution. The sampling distribution was this, all the possible results. And we figured out, we figured out the probability of each one of those results happening if everything is normal, if the null hypothesis is true, right? What we found, our statistic was, we found 2 turtles with metal weapons. Then we evaluated that based off the sampling distribution. The sampling distribution says the probability of getting 2 metal weapons is actually 0.25. Our alpha was 0.05. The probability of us getting our statistic should be less than alpha, should be less than or equal to alpha. If that is the case, then we would have rejected the null. But in this particular case, our alpha was 0.05. The probability of us getting 2 metal weapons was 0.25, so we could not reject the null hypothesis. We failed to reject the null. Now, you notice that we did a binomial in that first time, but do you remember how the binomial is only for categorical data that has 2 possible values and they're mutually exclusive, right? Well, remember I also gave you some other data. The other data was the number of pizzas that each turtle normally eats. Would we use a binomial for that? No, because binomial is only for categorical data that has 2 options that are mutually exclusive. 1 pizza versus 5 pizzas, that is continuous data. So we can't use a binomial for it. Well, it turns out that there are other statistics besides binomials. So let's start with this. Remember, this is the entire population. This is the entire population. The entire population, all of the possible Teenage Mutant Ninja Turtles, there are no others. What is mu? Mu is the mean for the population. In this case, the only mean that we can calculate is for pizzas, right? So I'm asking you, what is the mean for pizzas for this population? And in this case, it is 2.75, right? 2.75 pizzas. That is the mean. The reason why we use mu instead of x bar is because this is the entire population of Teenage Mutant Ninja Turtles, all of them, all of them. Now, mu is 2.75. There's a specific kind of sampling distribution. In this case, this is the sampling distribution of the mean. The sampling distribution can be for any statistic, and so we're going to do one for the mean. So the sampling distribution is all the possible values of a statistic. If the statistic that we care about is the mean, then the sampling distribution of the mean is all the values that the mean can take, along with their probabilities, if the sampling is random from a null hypothesis population. So we're going to do the same process we just barely did with the binomial, but now for the mean. So if you look at these right here, again, these are all the possible samples of 2. If n equals 2, all the possible samples of 2. So this is the same as what you saw before, but instead of looking at the result of metal weapons versus wooden weapons, we now have the mean. Now you can't see that bar on the top of the X very well, but that is an X bar, right? So if on day 1 I choose Leonardo, and Leonardo eats 1 pizza every day, and then on day 2 I chose Leonardo, and Leonardo eats 1 pizza every day, then the mean of Leonardo, 1 pizza, plus Leonardo, 1 pizza, the mean of 1 plus 1 is 1. 1 plus 1 is 2 divided by 2 days, right? That's what's going on. Leonardo eats 1 pizza every day. Donatello eats 3 pizzas every day. So 1 plus 3 divided by 2 is 2. So these are all the possible means that could happen when the null hypothesis is true. So does this represent the null or the alternative hypothesis? This represents the null hypothesis. I just told you. This represents the null hypothesis because this is what they eat every day. This is what's normal. This is what's normally going on. These are all the possible means for the population when the sample equals 2, n equals 2. Okay? All right, these are all of them, all of them. All right. This is the same data, but now I've replaced the names with how many pizzas they eat every day. And instead of day, I've called it try, or this try meaning like, think of it like a pulling out of a hat, right? Sampling from the population, I find the first try, the first turtle I took ate 1 pizza. Put him back in, next try, turtle ate 1 pizza. Okay, got it? So instead of looking at Leonardo, we're now looking at how many pizzas Leonardo ate versus how many Donatello ate, etc. So 1 plus 1 divided by 1 equals a mean. Again, this is a mean of 1. So the column of mean is exactly the same. All right. That's what we're looking at. Now, what is the mean of means? What is the mean of all the means? If you take an average of all the means, you are going to get 2.75. The mean of means is always equal to mu. Remember, we looked at this before. Come back. There it is. Mu was 2.75, right? That's the mean for the entire population. If you look at all the possible means, so this is all of the possible means, all of the possible means. There are no other ones out there. This is all of the possibilities because there's only 4 turtles, and if n equals 2, this is all the possible means. Then this, the mean of all of these means, has to equal mu. It has to. The mean of all of these means has to be the same as the mean of the population. In the sampling distribution of the mean, we call this the mean of means. So that, since we're talking about all of the possible means for the population, we still use mu, but it's mu sub x bar. So it's each of the sample means for all of the possible means. So the mean of the samples has to equal the actual mu, the actual one, right? So just to show you what I mean, the mean of all of these is 2.75. It is the same as this, 2.75. It has to be, every time. The standard deviation for the sample of means, we call that the standard error of the mean. And that is actually going to be standard deviation divided by the square root of n. We're going to talk about that in a later chapter. I just want you to know that it's not going to be the same thing for the standard deviation. That's going to change a little bit. But the mean of all of the means has to be the same as the mean. right? So the mean of all of the possible means of a sample of a certain size has to be the same as the population's mean. So let's take a look and do the same kind of hypothesis testing. So let's say that I think that gamma rays make turtles hungry. I took a sample of n equals 2. That sample of n equals 2 that I took had a mean of 4. Should I reject the null? So since this is a list, this is the sampling distribution, this is all the possibilities, right? So in this case, the statistic that I care about is the mean, and I calculated the correct statistic. It is x bar equals 4, right? So the mean number of pizzas for my sample of 2 people, the mean was 4. So what I want to say is, hey, is eating 4 pizzas, what's the probability of that happening when gamma rays don't have any effect on how hungry the turtles are? Well, lucky for us, this is a list of all the possible x bars. Remember, this is x bar. This is all the possible means when there's 4 people in the population and n equals 2. These are all of the possible means. So what we can do is exactly what we did with the binomial. We can say, hey, what is the frequency of each of the possibilities? So this is going to be a little bit different. It's going to look slightly different from what we did before just because there's more possibilities. So this is the possible means that we can get. The possible means can be 1. It can be 1.5. Whoops, where's my 1 go? There's 1. 1, 1.5, 2, 2.5, 3, 3.5. I need to move something over. Hold on just a second. 4, 4.5, or 5. These are all the possible means. Now remember, these are the means if the null hypothesis is true, if everything is normal. This is the normal amount of pizzas that the turtles normally eat. This is not if gamma rays are affecting anything. So what we need to do is we need to say, hey, what's the probability of each one of these happening? So that means we're gonna look at the frequency of each of these. All right. So here we go. Frequency. Frequency. All right. So let's make the frequencies be 1, 2, 3. Okay, what is the frequency of 1? How many 1s are possible if nothing's going on? Only one of them is, right? It's only 1. What is the frequency of 1.5? 1, 2. There's 2 1.5s. What is the frequency of 2? Let's count them. 1, 2, 3. There's 3 for the frequency of 2 is 3. Well, what happened to my 2? There we go. Frequency of 2 is 3. What's the frequency of 2.5? Let's count them up. 2.5, 2.5. I have 1, 2 of those. So 2.5 is 2. What's the frequency of 3? 1, 2, 3. What's the frequency of 3.5? It is 1, 2. What's the frequency of 4? It is 1, 2. What's the frequency of 4.5? It is 0, correct? We don't have any 4.5s. And what is the frequency of 5? It is 1. Okay. So let's make sure that this adds up. The frequency of 1 is 1. The frequency of 1.5 is 2. The frequency of 2 is 3. So that's 6 total. 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. All right. So what you're saying is we think that gamma rays are making turtles hungry. Now what you see right here, this is the frequency for each of these things. Each of these things. So for example, what we're looking at right here is what is the probability that you would get a 4? Or what would be the probability you get a 1.5? Or what was the probability you get a 2? But that is the probability if the null is true. If nothing is going on, if gamma rays don't have any effect. Gamma rays have 0 effect on your hunger. So when you look at this, so for example, the probability of getting a mean of 1 pizza from our sample of 2 is 1 divided by 16 possibilities. That's going to be 0.0625. All right? Okay, now we got an x equals 4. X bar equals 4. So the mean that we got was 4. So if you remember the steps for calculating, let's go back here. Where is the steps for calculating? Come back all the way at the beginning. Oh, there it is. We're going to calculate the appropriate statistic. The appropriate statistic was the mean. Then we're going to evaluate that statistic based on sampling distribution. If the probability of getting the obtained statistic or a more extreme value is less than or equal to alpha, then you reject the null hypothesis. Okay? We got a 4. So we need to see what is the probability of getting a mean of 4 or a probability of getting something more than 4. So we are looking at, come back, this. We need to get the probability of getting a 4, the probability of 4, and the probability of 5, because 5 is more extreme. What's the probability of getting a mean of 4 pizzas or more than 4 pizzas? That's what that says. And so what we're looking for in this particular case is the probability of 4, which is 2 divided by 16. So 2 divided by 16, because there's 16 possible outcomes. That's 1.25, plus the probability of getting a 5. So it's 0.125 was the probability of getting 4. 125. The probability of getting a mean of 5 is 0.0625. And so when you add those up, the probability of getting the mean of 4 or something more extreme is 0.125 plus 0.0625. 0.1875. So the probability is 0.1875. That is the probability of getting a mean of 4 or more pizzas if the null is true. If we chose our alpha as 0.05, then the probability of getting a mean of 4 or more pizzas is greater than our alpha. That means the probability of getting what we got and making a type 1 error is just too high. We would fail to reject. We would fail to reject the null hypothesis here. Would the probabilities stay the same if n equals 3? No. The probabilities would change. The bigger the sample, there's a change in probabilities. So that means that a sampling distribution is only the probabilities when you have that exact n. That's why in the binomial table, you see different probabilities for different n's. Okay? So the probabilities change based off of the number of people in the sample. What would it be a type 2 error for the gamma ray example? A type 2 error would be if we failed to reject the null hypothesis when the null hypothesis was false. So if we go out there and say, you know what, based off of this, we got a mean of 4, we can't say that gamma rays change the Teenage Mutant Ninja Turtles hunger, right? We don't have enough evidence. If we go out and say that, but in real life, gamma rays do change their hunger, that would be a type 2 error. All right, thanks everybody.